Now, how will we estimate the parameters in our VAR model? Well, like last week, we will use maximum likelihood estimation. We use a normal distribution for our error terms, and we will specify the log likelihood conditional on the first p initial observations. So we will make use of the conditional likelihood framework. And we will estimate our parameters based on our sample of t observations. Now, since notation quickly becomes cumbersome over here in our multivariate VAR model, we will make use of this compact notation, where the n-dimensional vector yt is regressed on all lagged values and a constant, which are all collected in this vector xt over here. And the matrix P then collects the pi, then collects all the constant terms and the autoregressive parameter matrices that need to be estimated. In your tutorial assignment, you will actually dive into the derivations of the log likelihood for the VARP. Again, you will need to start from the log of the joint density, which you can then express as a product of conditional densities. The likelihood of the full sample conditional on the initial observations is then nothing more than the product of the individual conditional densities. Now, once we have obtained the expression for the log likelihood, we need to find the value of our parameter pi that maximizes the log likelihood. Now, since only the last term here in our objective function depends on capital pi, well, the log likelihood is maximized when this term over here is minimized, since we have the minus sign in front of it. So let's have a closer look at this term. And let's first make an abstraction of omega here in the middle. Then what do we have? Well, we see that we actually have a sum of a squared term. And in the parentheses, we have nothing more than the residuals of our VAR model. So we need to minimize a sum of squared residuals. Now, this should ring a bell from previous courses, since this is exactly the objective function we had to minimize to obtain our classical least squares estimator in the regression framework. And indeed, our maximum likelihood estimator of the VAR is nothing more than our classical least squares estimator obtained by running least squares regression equation by equation. So by regressing y1 on all the lagged values to get its corresponding parameter coefficients, then regressing y2 on all the lagged values to get the coefficients in the second equation, and so on, all the way up until the last equation. Now, of course, we still need to show that this value of pi maximizes the log likelihood for any value of omega. And that is what we will do on the next slide. Let's start from the expression that we need to minimize. So the sum of squared residuals, where we have omega inverse here popping up in the middle. Since we need to prove that the maximum likelihood estimator of pi maximizes the likelihood for any value of omega, we of course need to bring it in somehow. And that is what I do in the first equation over here. I subtract and add the term with pi hat, the maximum likelihood estimator. And I do that, of course, in both parentheses. Now, yt minus pi hat times xt, that is nothing more than our residual, so the epsilon hat on the next line. I write out this residual, and the remaining terms in the axis I regroup together. Okay, so that is what I do in this line. To arrive now at the next line, just expand the terms that you have. And then I get this squared term for the residuals. I get the cross term over here. And then I have the squared term for the x's. Now I've highlighted this term here in the middle in red. Why? Since it is equal to 0, so we can drop it. First, let's say that you believe me that this term is indeed 0. Since then we continue here with the derivations on the slide. And on the next slide, I will then convince you of the fact that this red term is indeed 0. So leaving out this 0 term, we are then left with these two terms over here. And to arrive at the next line, I just simply define a new variable x star as this product over here. Now the first term is then just the quadratic term in the residuals. And the second term becomes a very similar quadratic term, but the quadratic term in the x stars. Now these quadratic terms will always be positive since we have a quadratic form here for the x stars. And omega inverse is a positive definite matrix with positive eigenvalues. So if the last term is larger than or equal to 0, positive, the smallest we can make our objective is when this last term would be 0. And when would this term be 0? Well, when pi would be equal to pi hat. So our least squares equation by equation estimator. So that proves then that the objective function is minimized here, or the log likelihood is maximized by taking pi equal to pi hat, and this regardless of the value of omega. Okay, so we achieved our main objective, but I still need to convince you of the fact that this term in red over here is indeed 0. So let's take a closer look at this term on the next slide. First of all, convince yourself of the fact that this term is nothing more than a scalar by inspecting the dimensions of all terms involved. The residual vector is of dimension n times 1. So its transpose is a 1 by n vector. Omega is n times n. The vector x has only one column. Indeed, we have a scalar. Now, since this is a scalar, I can simply apply the trace function to it, and I get the same scalar again. Why do I apply the trace? Well, since it has this nice cyclic property as summarized in this footnote. The trace operator remains unchanged if you cycle the inputs around by placing the first one at the end and so on. So I can place my residual vector over here, the first guy, to the end, and nothing changes. On the next line, I then take the matrices that do not depend on T in front of the sum, and I'm only left with the cross product over here of the predictors and the residuals. Now, since these are the residuals from an OLS regression, they are by construction orthogonal to the explanatory variables. That's exactly as set up under the first order condition. So this cross product over here is indeed 0, and hence the entire term is 0. Now in the tutorial assignment, you will have a closer look into the derivation of the maximum likelihood estimator by making use of matrix derivatives. To this end, I've summarized here some useful matrix derivatives on this slide, where the gradient over here of a function of x is given by this vector, where in essence, you take the derivative with respect to each component in x. Similarly, for the matrix derivative, you take the derivative with respect to each entry in A, the matrix A. Now, so far, we derived the maximum likelihood estimator of pi, and we have shown that it maximizes the likelihood for any value of omega. Knowing this solution, we can then continue to solve for the maximum likelihood estimator of omega. And to this end, we work with the so-called concentrated log likelihood, which is the log likelihood with the value of the estimate for pi plugged in. And it is this concentrated log likelihood, denoted like this on the slide, that we will now maximize with respect to omega. In your tutorial assignment, you will first show that the concentrated log likelihood takes on this form. And we should then continue maximizing the concentrated log likelihood over all symmetric positive definite matrices, since omega needs to be symmetric and positive definite. Luckily for us, as we will see in the tutorial, the solution for an arbitrary n by n matrix already turns out to satisfy these properties. And so the maximum likelihood solution is just given by the average squared residual, as you will see in the tutorial. On the diagonal, we have the average squared residual of the ith regression. And on the off diagonals, we have the average product of the OLS residuals between variables I and j. Now in the tutorial, you will derive the maximum likelihood estimator for omega. And to that end, you again need to use results from matrix derivatives as summarized here on the slides. With all of these results, we are now ready to establish some nice properties of our estimator, namely the asymptotic normality. So under stability of the VAR and some moment conditions, one can indeed show that we obtain here this asymptotic normal distribution. The asymptotic variance is given here by this Kronecker product of omega and Q inverse. So this is the symbol for a Kronecker product. What is a Kronecker product? In essence, you blow up each entry in the first matrix, so in omega over here, with the second matrix, so Q inverse, as shown here at the bottom of the slide. To establish this asymptotic normality, there are a couple of key steps that you need to take, and we will be deriving such results extensively as of next week. On the next slides, I provide a high-level overview of the key steps, a roadmap of steps to follow. And we will fill in these, the details of each of these steps as of next week on. For today, it is just important that you understand the key steps that are involved that you need to take. First of all, start from the definition of the estimator, where the coefficients for the ith equation of the VAR are obtained through this formula of the least squares estimator. Then we continue by plugging in the DGP for YIT, as indicated in blue over here, which is nothing more than x times pi I plus the error term. After expanding these terms, we are left with this expression. And after some rearranging, we see that the red terms, of course, can be crossed out. And after bringing pi now to the left-hand side, this actually disappears, so you can simply bring pi I to the left-hand side. We arrive at this bottom expression over here. Now, to arrive at our asymptotic distribution, we need to introduce appropriate scaling, which means that we need to blow up this difference over here by its asymptotic rate, which is root t, as you might remember from the classical regression framework. If you now multiply by root t on the left-hand side, we also need to do that at the right-hand side. And I immediately place the correct scalings on the two individual terms. From your regression course, you might remember that the first term needs scaling by 1 over t, since we will use the law of large numbers, abbreviated here like this, on this average. The last term is a scaled average and needs scaling 1 over root t to make use of the central limit theorem, abbreviated like this. For the VAR, the law of large numbers and central limit theorem will also be our key ingredients, but we will need versions of them for dependent processes. So we will need a law of large numbers for dependent processes to show that this average converges to its population analog. And second, we need a central limit theorem for dependent processes to show that this last guy over here converges in distribution to this multivariate normal. We will dig deeper into this law of large numbers and central limit theorems for dependent processes as of next week. Now, in the last step, we need to put all of the pieces together. And I rewrite here my left-hand side, let's say with this matrix notation. I've shown already convergence for each of these terms on the previous slides. So for the last one, I know that this guy converges to a normal distribution. So this entire term, which is nothing more than a kind of rescaling of this last term, will also converge to a normal distribution. How can you determine the asymptotic variance of this normal distribution? Well, to determine the asymptotic variance, you can rely on the continuous mapping theorem. I start from the asymptotic variance of this guy over here, the blue one from the previous slide. And then I have this kind of sandwich form, where the continuous mapping theorem tells me that I can pre and post multiply by the probability limit of this first red term. And QT indeed converges in probability to Q, so its inverse converges in probability to the inverse of the population analog. Then, making use of some rules for Kronecker products, the first term is simply here the omega matrix, and the second term is the inverse of Q. And this concludes then the derivation of the asymptotic normality in our first video.